In this short video, we're going to review some terms that will be very helpful as we study how things move in and out of cells and back and forth between solutions. And the first term we need to talk about is a term called tonicity. Tonicity refers to the relative solute concentrations between two solutions. Basically, we mean how much dissolved stuff. Now, there are three descriptor terms we're going to use. Hypertonic. The word hyper, or the prefix hyper means above. So we have hypertonic, which means more dissolved solutes. We're going to have hypotonic. Hypo means below. Think hypothermia or hypodermic. A hypodermic needle goes below the skin, so hypo means below. So it's going to be less dissolved solutes. And of course, we can have isotonic, where iso means the same. Now notice how I wrote this. More dissolved solutes than, the same amount of dissolved solutes as, or less dissolved solutes than. And the reason I make that obvious is because of this. If I were to give you a solution that, say, here's a solution and I tell you it's 90% water and 10% solutes, maybe it's salts or sugars or whatever, and I ask you, is this solution hypertonic, isotonic, or hypotonic? You can't answer because it has to be in comparison. Is it hypertonic than something, or hypertonic than something, or the same as something else? I have to have another solution to compare it to. So no solution is hypertonic in isolation, or hypo or iso. So here I have two solutions, solution A and solution B. How did these two solutions compare to each other? We would say that solution A is hypotonic as compared to solution B, and solution B is hypertonic as compared to A. Again, it has to be in comparison. So we'd compare the amounts of dissolved solutes, 5% to 15%. So side A is hypo, it has less, and side B is hyper, it has more when compared to the other solution. Now we have to be careful because it's referencing the amount of solutes, not the amount of water. If we were referencing the amount of water, we wouldn't use the term tonicity, we would use something like water potential, but in that case we got to be careful. So always reference with tonicity the amount of solutes, not the water. Now if we clarify that this boundary between these two solutions is a selectively permeable membrane, the next question is, which way does water want to move? And by what process? Well, in this case we can just look at the amount of water and say that water is going to tend to move from areas of higher concentration to areas of lower concentration, and the process would be, of course, osmosis. But one of the things we can generalize is we can say that water is going to always move towards the more hypertonic region. So since this side has more dissolved solutes, water is going to be drawn towards that side. Let's look at another situation where we're looking at cells. So let's look at this and make this a little here. Here we have 4 different solutions and 2 different cells. I have an animal cell and a plant cell. This represents the cell wall around here. So the question is, what will happen if I place each of these cells into each of the solutions above? Well, let's look at it one at a time. If I take the animal cell and I place it into this solution, how does the solution compare to the cell? Well, the solution is hypertonic compared to the cell. It has more dissolved stuff. But the more interesting question is, which direction will water move? Is water going to move into or out of this cell? Well, water always moves towards the more hypertonic region. So in this case, water is going to move out of the cell, and this cell is going to lose volume quickly as it loses water to its environment. What if I move this cell into this solution? How do the two solutions compare? How does the solution compare to the cell? And in this case, they're isotonic. So which way will water move? Now you might be tempted to say that water won't move, but in fact it will. It'll move in and out at the same rate, so we'll see no net change. Let's go to the next one. If we take this animal cell and place it in this solution, how does the solution compare to the cell? Well, this solution is hypotonic when compared to this cell, so which way is water going to want to move? In this case, water will move into the cell and cause this cell to swell. It will gain water as water moves in towards the more hypertonic region. Our final solution is 100% water, which is always the most hypotonic you can get. It has 0 dissolved solutes. And so we should know by now that water is going to want to move in. And it could move in such an amount that this cell, this animal cell, swells up so much that it bursts. The cell could fill up so much that it basically just explodes. We call that lysis. Now what happens in the situation where with the plant cell? Do things happen differently? Let's take a quick look. Now this plant cell has the same concentration of solutes as an animal cell, so in terms of the way the water works, we're going to have the same things occur. When we place the plant cell in the hypertonic solution, it's going to lose volume. Water is going to leave this cell and go out, and what will happen is the cell membrane, this black line, will shrivel up and pull away from the cell wall, but the cell wall really won't change shape too much. That process of the cell membrane shriveling up and pulling away from the cell wall is called plasmolysis. If we take this animal cell, or plant cell rather, and put it into the isotonic solution, again we're going to have water move in and out and at the same rate, so we see no net change. If we move the plant cell into a hypotonic solution, let's talk about what happens here. Water will definitely move into the plant cell as it moves towards the more hypertonic region, and now the cell membrane is going to swell and press up against the walls, against the cell wall, and the cell will become turgid, or it builds turgor pressure. As this cell membrane presses up against the cell wall, we say that the plant cell becomes turgid or tight. And the same thing would happen as we move that plant cell into the pure water solution. Again, water is going to move in, but unlike the animal cell, the plant cell doesn't risk bursting. That won't happen. It will just build more turgor pressure because that cell wall will protect the cell membrane from getting too big and bursting. So there we go, a quick video on tonicity and how it affects the movement of water in and out of cells based on relative solute concentrations.